finish out our talk on radical equations with a short video, or it might be a long video, on applications. There are a few prerequisites. Sorry, my handwriting is a little bit bad right now. Just under the weather, not doing very well. But anyway, the prerequisites here: problem-solving process. You need to know the problem-solving process, and if you don't know the problem-solving process, you might want to look at one of my many application videos that I have. It all basically comes down to that you have to first read a problem, then you need to understand really the situation. And these are more of rules of thumb. You can kind of break out of this after a while. Always you should try to label unknowns. Each of these are kind of the easy steps. Well, maybe not understanding the situation. Fourth thing is to write equations with those unknowns. Fifth thing is to solve these equations. And finally, check your result and state the answer. So check and state. Alright. You also need to know everything about radicals and exponents. Pretty much everything in intermediate algebra has to offer about radicals and exponents is fair game. And you should know how to solve a radical equation, any type of radical equation that's handed to you. Now, as with most applications, there's obviously a level of mathematical maturity required and also a level of intellect required. You need to be able to decipher what a problem means. And if you don't know something, you should always Google it or try some other way of looking it up. Go to the library or whatever it is. Now we'll start kind of easy on ourselves. Even though this has a lot of words in it, it actually is an easier word problem. The period of a pendulum is the time it takes for the pendulum to complete one entire swing from left to right and back again. So you can kind of think of like a grandfather's clock that has the pendulum like this. The period is the time it takes to go all the way to one side and all the way back. Okay, tick tock. Okay. Let's see. The greater the length of the pendulum, so this is the length here, L, the longer its period. In other words, the longer it takes to go through one cycle there. In fact, if L is measured in feet, then the period is given in seconds by this formula. So, all this is kind of set up. The time it takes to go through one period, which is just back and forth and back again, so left and then right, is equal to 2 pi times the square root of the length in feet of the pendulum divided by 32. So suppose you're standing in the convention center in Portland, Oregon, and you time the period of its Foucault pendulum, which is the longest pendulum in the world. Its period is approximately 10.54 seconds. So that's how long it takes to go from left all the way back to right. Approximately how long is the pendulum? Well, I've read the problem, I understand what's going on, and in this case, they're letting me know that t is equal to 10.54 seconds. One thing you need to do with all application problems is if you're given a formula, make sure that the numbers they're giving you are in the right units. So let's take a look at this. Let's see, the period given in seconds. So they gave this as in seconds. We're absolutely fine. So we can find out the length of the pendulum. Let's go ahead and let t equal 10.54. And that should equal 2 pi times the square root of L over 32. And if you look at this, there's actually only one variable in this problem, this L right here. Let's ask ourselves what happened to L. So we can unlock it. What happened to L? And again, I normally don't do this when I'm solving an equation because I'm so used to what to do, you know. But eventually I'm going to stop writing down all these little what happened to L, what happened to whatever. But it's good to see this over and over again initially. So the first thing that happened to L, here's L, it gets divided by 32. Next thing, after it gets divided by 32, somebody took the square root of it. And then finally, they multiplied by 2 pi. Notice I just kind of grouped these together because it's 2 pi times that. So now let's undo that. You always untie a knot by starting with the last thing that was done and undoing it. Undoing multiplication is division. So we're going to divide by 2 pi. And then undoing the square root, we're going to square both sides. And finally, undoing division by 32, we're going to multiply by 32. So here we go. Divide both sides by 2 pi, and you will get this. You'll get 10.54 over 2 pi. Notice that I'm not really reducing that at all because I know I'm going to have to grab a calculator in a moment. So I'm just going to go ahead and leave that be. I'm not going to grab a calculator. Good rule of thumb in mathematics, don't grab a calculator until the very end of the problem. Okay? Let's see, the second thing I need to do is square both sides. So I'll go ahead and square this side, square the other side. So that is going to give me that L over 32 is equal to this number, 10.54 over 2 pi, being squared. And now, notice I still haven't actually grabbed a calculator. Now to solve for L, I multiply both sides by 32. I've already done that. Now we're about to multiply both sides by 32. Multiplying the left side by 32 cancels 32 in the denominator, and you get L is equal to, and then 32 times 10.54 over 2 pi being squared. And again, don't grab a calculator until the very end of the problem, which is actually right now. So we'll go ahead and do it. 32 times the quantity, 10.54, divided by pi. So let's see, second pi. Oops, no, it's 2 pi. Let me go back there. Oh yeah, we're dividing by 2 pi. So when you divide by something more than just a single number, you have to put a parenthesis. 2 pi. And end that parenthesis. This tells a calculator you're dividing 10.54 by the entire expression 2 pi. Finally, finish out that outer parenthesis and square it. And you will get 90.047. We'll just round it to the nearest foot here and just say it's 90 feet. Roughly 90 feet. Not bad. Now this next problem looks like a doozy. It's quite a bit to it. This is what's known as a concept mastery problem. It just has a lot of questions to it. It's my favorite style of problem really to give to students because I think that asking something, just one thing about an application is useless. It's better to say, here's an application, now here's a million questions about it, because you get to delve into it. So, a UFO is hovering directly over your head at an altitude of 700 feet. It begins descending at a rate of 10 feet per second. At the same time, you start to run at a rate of 15 feet per second, just because you're freaked out. Now, each of these questions is kind of a baby step process. And by the way, this question is from the Yoshiwara textbook, Modeling Graphs and Functions, available at lulu.com. It's an intermediate algebra textbook. Anyway, all right. Each of these problems is just a little step. Okay, so let's draw a picture of this situation. We have a UFO hovering 700 feet above, and then it starts to descend at 10 feet per second. So let me just see if I could draw a nice picture of that. Don't know if I can, but I'll try. So here's a UFO. I think they usually have these types of tops, right? That's what everybody says with that. And let's pretend that this distance is 700 feet. Here's the ground right here. And it's right above me, or you, or whomever you want. Okay? But 700 feet from this point on the ground. And it starts to descend at 10 feet, what do we say, per minute or per second? Per second. I guess it'd be very slow if it were per minute. It'd be like one of the hoopties. 10 feet per second. And you freak out and start running away at 15 feet per second. So you're really freaked out. Let's see. What's the altitude of the UFO so many seconds later? Well, let's see. Initially, and this is what's great about mathematics, you can make a table of values to kind of see the pattern. Here's the time that's passed, and here's the altitude of the UFO. If no time has passed, what is the altitude of that UFO? 700 feet. I hope somebody kind of whispered it in their brain. Okay. 1 second later, it's dropped 10 feet, so it should be at 700 minus 10 feet, right? 2 seconds later, it dropped, a lot of people say 20 feet. It dropped 2 sets of 10 feet. In other words, it was at 700, but you lost 2 of those 10-foot increments. 3 seconds later, you're at 700 minus 3 of those 10-foot increments, and so on and so forth. In fact, t seconds later, you're at 700 minus 3, whoops, not 3, minus t times 10. Just noticing the pattern, right? If you look at the pattern here, 1 matches up with a silent 1 on here. 2 matches up with the 2. 3 matches up with this 3. So t must match up with this t. So that's the altitude t seconds later. So the answer to the first part is going to be that the altitude is 700 minus 10t. You can test it out. 1 second later, it's 700 minus 10 times 1. How far have you run t seconds later? Well, again, go to the picture. That kind of helps out. And we'll make a little table for this. So t seconds, and we'll say d is the distance you've run. Or maybe we'll let r equal the distance you've run. Well, initially, you're no distance away from your initial spot. You're just right there. 1 second later, you're 15 feet, right? And 2 seconds later, you're 2 of those 15 feet away. And 3 seconds later, you're 3 of those 15 feet away. So, obviously, t seconds later, you're t of those 15 feet away. Or in other words, you're 15t feet away. So let's go ahead and write that in. How far have you run in t seconds? Well, 15t feet. Sketch a diagram of your position and the UFO at time t seconds. Well, we already kind of sketched a diagram, but let's just say that t seconds have passed. And by the way, t is a variable, so I have no idea what that means, right? But it basically means I ran over here, it's dropped down to like here, let's just pretend. Okay? So here's after t seconds. So this distance right here is 15t, and this distance right here is 700 minus 10t. Because again, what is the altitude of the UFO? So that's the altitude, 700 minus 10t. Okay? Basically, it's losing height as time goes on. All right, label and sketch with your answers to parts. Oh, well, we already did that. So I'm going to put a little check mark on that saying we've done it. Yay for us. Express the distance d between you and the UFO as a function of t. Okay, so let's try to get a hold of what we're talking about here. They're asking us to find this distance d. Well, if you look at this picture, actually, isn't that a right triangle? So we have a right triangle, and we have a length of one side, we have a length of another side, we're missing the hypotenuse. That's the Pythagorean theorem. Right there, once I see a right triangle, I immediately think Pythagorean theorem. So let me go ahead and erase all this other junk on this page so I can do some calculations. And remember, they want me to express the distance in terms of t. Well, hypotenuse squared should equal to side length squared plus the other side length squared. And if we look at the actual question, it says express the distance as a function of t. Well, that means I have to solve for d. And d is almost solved for. I just need to take the square root of both sides. It used to be, and it still is in mathematics, that when you take the square root of both sides, you get a plus or minus. 15 squared is 225 t squared, and I'm just going to leave this as plus 700 minus 10t and cross my fingers and hope that I don't have to do anything else with it. But one thing I want to mention here, distances are never negative. So we don't have to actually worry about the negative. In application problems, you almost always can throw out the negative value, because the negative value, you're usually asking for how long it took for something to happen, or how far away are you, or something like that. And that just won't be a negative number. So we're back here. Check that off. What is the distance between you and the UFO when 10 seconds have passed? Well, since the distance is just equal to this formula over here, or this expression, I'll let t equal 10 seconds. And I'll substitute that in and do some mathematics here. So let's go ahead and plug this in. We get d is equal to the square root of 225, and then 10 squared would be 100, so with a couple more zeros on there. Plus, and then 10 times 10 here will be 100, so it's 700 minus 100, or in other words, 600 being squared. 600 squared is just going to be a nice 36 with 4 zeros behind it. So we'll just write that in. 225,000 plus 36 with 1, 2, 3, 4 zeros on it. And at this point, I'll probably just grab a calculator to finish this out. And that looks to me, by my calculations, to be this 618, roughly. That's rounded to the nearest. What is that distance going to be? We're talking feet in every direction, so this must be 618 feet, because those were the distance, the units on the distance there. Now part F here has to deal with a graphing calculator, so I should probably open up a graphing calculator. There we go. It says graph your function in the window 0 to 94 and 0 to 1240. So that's a good example to kind of really get used to our graphing calculator. So let's go ahead, and here's our function here. It's a square root. So remember, to graph anything, it's all these blue buttons up here. You hit y equals. Clear out anything that you have there by hitting the clear button. And then we want to type in the square root of all that business. So here I go. I'll hit second to access that square root. It already puts an initial parenthesis in. 225 times x squared. And then plus, and I'll just put this as the quantity 700 minus 10t, or actually x, and that quantity was being squared, and then I'll end the parentheses on the square root. So that's the function. And let's see, I seem to recall they told me to adjust the window here. So let's go ahead and check what they told me to adjust it to. Yes, they told me to adjust this from 0, the minimum x value is 0, the maximum x value is 94, the minimum y value is 0, and the maximum y value is 1240. Okay, and hit graph. Well, that's kind of neat. Okay, so remember what this is giving us. The inputs here, which are on our graph, are x, but in reality they're supposed to be t's. Inputs are time in seconds, and the outputs, let me just go to the second page here, the outputs will be the distance away that the UFO is from me or you as we're running away. So as time ticks on, the distance between me and the UFO, or you and the UFO, whichever, gets down to a minimum, but then as I continue to run and it begins to land, I get further and further away from it. Remember, the vertical values are the distance aways. Now it does say verify your answer to part E on the graph, and remember our answer to part E is that when t equals 10, we're roughly at 618 feet. You can do this one of two ways. You can just type in Well, actually, I think you have to hit the trace button. So if you hit the trace button here first, it gives you coordinates, and you could type in the number 10 and hit enter. And you'll see that the y value, which corresponds to our distance, is 618, roughly. And then use the graph to find the distance between you and the UFO when t is equal to 45. So again, I'll just type in 45. And there we are. Distance 45 seconds later is 719 feet. Pretty neat. You could do this, you could extend out this graph and you can find a distance between you and the UFO at 60 seconds. Right? It's pretty neat. Okay. When is the distance between you and the UFO the smallest? And then it does say use the graph to estimate the nearest second. So the distance again is represented by the heights, and this is just asking when are the heights on this graph the lowest. So that happens to be in this region right here. And on a graphing calculator you can calculate the minimum of a curve by using the menu above the trace button here. To access that calculate menu, you hit the second button and then trace. Second accesses everything in yellow, and I want to access the calculate button. And then notice the third option there is a minimum. I want to calculate a minimum. So I select that. And it says what's the left side of the minimum point? So I have to just go to the left here until I get to the left side of the minimum. I give myself a little extra room. So that's the left side of the minimum. Now it says where's the right side of the minimum? And notice it has that little arrow up above. This little arrow right here. That's just telling me that's where my left endpoint starts. I'll select this as my right endpoint. So it's going to guess between these two values where the minimum is, and I'm going to take a guess that it's right about somewhere around here. I'll hit enter, and it's actually going to calculate it exactly. Let's see. When is the distance between you and the UFO the smallest? When means like how long. That's a time value. And so that'd be 21.5 seconds, and we want it to the nearest second, so 22 seconds. So that's what it is. So let me just write in here 22 seconds. Roughly, very roughly. Right? And by the way, that minimum distance is 582 feet. And then part H, it says actually the window that we used right here, what you see, is too big. Find the domain of the function d and change x max to a more realistic value. Well, it's kind of the hint is what this is all about. The fact is that this is assuming that the UFO keeps going down and down and down and down and down, even below the ground. But the fact is the UFO doesn't go below ground, right? The UFO will eventually, let me move this over, the UFO will eventually hit the ground. So it's probably good to ask how long does it take for the UFO to hit the ground? Let me do that. How long until the UFO lands? Well, that means, remember the altitude of the UFO is this, 700 minus 10t. We just want to know when is that 0. I'll add 10t to both sides. Divide both sides by 10, and I get this. T is equal to 70. So 70 seconds, it takes 70 seconds for that UFO to land. I have 70 seconds of running until they land and destroy everybody on Earth. So let's adjust the window here to not go to 94 seconds, but instead just to 70. Now, it doesn't really do anything for us other than just give a realistic domain of our function, because from that point on, your distance is just how quickly you're running. So it's a kind of an interesting kind of side problem. Let me make sure that we answered everything about this. Yeah, we answered everything about this question. Very good problem. And notice that in this problem, there were just a lot of little questions that we had to answer and everything. It's just so important that you're able to analyze your way through a problem. No matter how difficult you may think it is, you should be able to work your way through a problem like this. Now, as a final example, we'll take a look at this. This is a more complex word problem. You actually do see this kind of word problem in a calculus course. oddly enough, but we can actually do part of it here. So the telephone company is laying a cable from an island 12 miles offshore to a relay station 18 miles down the coast. So 12 miles off the shore. So this is a top-down view of the world. And here's the island. And it's 12 miles from the island to the shoreline. And then from that spot that's directly 12 miles from the island to the shore, from there, if you walk 18 miles, you get to a relay station. Okay? It costs $8,000 per mile to lay the cable underwater and $3,000 per mile to lay the cable underground. The telephone company would like to find the cheapest route to run their cable. This is a very real-world style problem. The fact is, do you want to run all the cable underneath the water perpendicular, just get directly to shore as quickly as possible? Because, well, you're spending a lot of money, right? If it's $8,000 per mile, man, I know that this hypotenuse right here is much longer than 12 miles. So wouldn't it be cheaper for me to just lay the cable, the expensive part of it, this shorter distance of 12 miles, and then lay it along the shoreline from that point forward at $3,000 per mile? But actually that's not true. There's a cheaper way. There's a way to find out the lowest cost, or the minimized cost. So let's take a look at how we're going to step our way through this, and all of these should be given to you in an algebra course. At this point, these types of problems are so complex that you do have to kind of walk through step by step. So how much would it cost to run the cable directly to the shore and then 18 miles along the shore to the station? The question is asking, how much would it cost us if we did that one scenario I was just mentioning, where we start right here at the island and go all the way to the shoreline, and then go from the shoreline all the way to the relay station right there. Okay. So, well, we know that it would cost, so the answer to part A, we know it's 12 miles at $8,000 per mile. That's for the first part of it, the underwater. And then to that, we're going to add 18 miles of cable at $3,000 per mile. And if you look at this, the word at in reality means times. So let's go ahead and replace that symbol, that at symbol, with times, multiplication symbols. The words miles will cancel in this first term here. So let me cancel the word miles. And you have 12 times 8,000, which is 96,000. So let's go ahead and write that in. So the first thing is $96,000 plus, and then 18 times 3, I think that's $54,000. Oh, and by the way, yes, the words miles back here also cancel. So 18 times 3,000. So altogether, it's going to cost us, what is that, $150,000? $150,000. Okay, that's how much it would cost to lay it if you went in perpendicular directions. Now, part B asks a very interesting question. How much would it cost to run the cable directly to the station, but entirely underneath water? So I'm going to fill this in, by the way, just so that we have a running tally of how much things cost. So for this part, we're just asking how much would it cost if I just ran the cable directly to the relay station, but underneath the water the entire time? Well, if you look at this, this creates a triangle. A nice right triangle, in fact. Let me go ahead and just show you. There's one leg of it right there, and then we have another leg of it right there. It creates a nice right triangle, and so we know that Pythagorean Theorem says, so let's go ahead and use the Pythagorean Theorem here. And let's see, we have leg squared plus leg squared should equal that distance underwater squared. I'll just call that D. That distance underwater squared. Well, 18 squared, and I'm actually just grabbing a calculator really quickly because I don't have that memorized, it's 324. 12 squared is 144. And now we'll go ahead and add those two up. So again, I'm just quickly doing this. 468 is equal to d squared. So therefore that distance, if we were to do it underwater, would be equal to plus or minus the square root of 468. But again, distances are never negative, so you can always take that off when you're dealing with real problems. So the distance is roughly, in this case, if you take the square root of 468, 21 point, I'll say 0.6. It's about 21.6 miles is the distance there. Now, I didn't really mention it, but the fact is we need that distance so that we can determine the cost of running that. So we're going 21.6 miles at $8,000 per mile. So 21.6 times the $8,000 per mile. It's a weird looking multiplication. And when you do that, let's see, I'm actually multiplying my the number that I have. You can't see my calculator, but I'm multiplying the really well approximated 21.63333 by 8,000. And it comes out to be $173,066.46. That was me actually, again, using my calculated better version of that. So you can see how expensive it is, right? We think, if you run it straight from the island to the shore and then the shore to the relay station, that's 150,000. If you run it directly underneath water, that's 173,000. So we would like something less than both of those if we could. Now part C is what really is going to happen. The phone company is going to run the cable from the island to some intermediate point, not directly in the center, but some point on the shoreline, and then continue laying the cable along the shore. So the distance from the relay station to the point Q will be 18 minus x miles, and express the cost of laying the cable as a function of x. And it gives me steps. I'm actually going to not follow those steps because I can kind of do it without those steps. Here's the deal. If this whole distance is 18, and we call the distance from here to here x, well, then the remaining distance has to be 18 minus x. If you add these two together, you'll get 18 minus x plus x is 18. So this total distance is still 18 miles. It's just we don't know how much we've kind of left out here. Now to talk about the cost that's gonna incur for laying this cable under the water here, we're gonna have to find that distance. So the total cost is going to be, well, cost for underwater, and then I'll say underwater, plus cost for underground, which is obvious, right? And this is how you want to do a lot of math problems. You break it apart into little bits like this. What's nice about the cost for laying the cable underneath water is we know it's $8,000 a mile. $8,000 per mile, and then times the number of miles in water. Plus, well, we know the cost for laying the cable underground is $3,000. And we just are going to multiply that by the number of miles underground. See how slow I am with doing this. The reason why I do this very slowly is so that we can really get into the meat of the problem and kind of see what's happening. So this miles underneath water here, that's this distance from here to here. I want to know that distance. Well, if you take a look at the problem here, this is a right triangle. This little bit, that's a right triangle. So that tells me that that distance, I'll call that distance C for cable. That distance C can be found if we use Pythagorean Theorem. Pythagorean theorem says 12 squared, that's leg squared, plus x squared, that's the other leg being squared, should equal that distance squared. And of course, we don't want to know what the square of this distance is. We want to know what the actual distance is. So that actual distance is plus or minus the square root of 144 plus x squared. And of course, it's a distance, so we can forget about the minus. Okay, it's just going to be a positive square root of 144 plus x squared. That's the distance right there. So at $8,000 a mile, we are going to lay the cable for this many miles. Square root of 144 plus x squared. That's the number of miles underwater. Plus the $3,000 per mile for laying it underground. And the number of miles we've laid underground is actually this distance from here to the relay station. That's 18 minus x miles. And that right there is a function. Let's say we'll have a total cost, so t of x, that's what I'll call it, t of x, is my total cost function. And I'm inputting x, which is just the distance along the shore that I pipe to. Okay, so as a final answer, I'd probably write this, 8,000 root 144 plus x squared. And then plus, I suppose you could distribute the 3,000 through, but I'm not going to. I'm going to leave it like this for now, because I have an idea that maybe I can leave it like this. It might work out nicely. Now, if you look at part C there, and if you read through all the extra steps, that's exactly what we did. So you can read through that if you want, but I've already done it. Part D is asking us to graph the function in the window, let's see, -10 to 20. So let me adjust my window while I have it on the screen. -10 to 20 and 0 to 200. So y equals 0 to y equals 200. When you do this, you always have to keep in mind what the x's represent and what the y's represent. And the easy way to figure this out is to go back to the previous page and look at our function. Our x's represent the number of miles away from, well, maybe I need to move this. X is just this distance right here. Okay, so it's the number of miles that we're going to pipe the cable underwater to. And that's the number of miles off between directly going to the shore and kind of going offshore. That's that distance right there. So we're saying we just want to see if we let x equal -10 all the way to +20. -10 doesn't make sense. I don't want to go backwards. But we're saying that this distance can be up to 20 miles. Is that realistic? No, because we only have 18 miles really to give. But that's what the problem states, so we'll do it. The y values, on the other hand, let me move this out of the way so we can see the y values. The outputs are the total cost. Now notice that y minimum is 0 and the y maximum is 200. I have a feeling this is not going to graph very nicely. And as I just reread through that part C, I see why our function is going to be a little bit awkward for this, because they, in this problem, ask us to represent or let the function represent the cost in thousands of dollars. So let's adjust our function here. If we want to adjust it, right now it's giving us the true dollar cost. But if we want it just in thousands of dollars, I'll divide each of these terms by 1,000. So in reality, I'll just make a new function. I'll call it f of x. F of x is equal to 8 root 144 plus x squared plus 3 times 18 minus x. That's actually the cost in thousands. So when I plug in an x value, I'll get out an output that represents the number of thousands of dollars it's going to cost to start piping at that distance. So now we're going to actually graph this function. Clear out any graphs that you have. All I did was hit y equals to get to this. Type in 8 times the second square root of 144 plus x squared. You can use either the square button or the raised to the second power button. It doesn't matter. And that square root. Add 3 times the quantity 18 minus x. And now if I hit graph, you'll see that the total cost starts kind of high and it goes down, down, down. It gets to a low point and then it starts rising. This low point is what we're interested in. We want to know what is the x value that's associated with that low point. I'm going to guarantee it because, well, that's just generally how all these problems work. So if you look at the next question, in fact, locate points corresponding to answers A and B. Well, you could do that just by typing in 150 and 173. If you want to do that, you hit trace, type in 150, hit enter. Oh, well, interesting. I wonder why that's not valid. C. And the reason is because I'm plugging in for X. And when you're plugging in for X, remember the dollars are the amount of the cost is the output. What we're plugging in here is how far away from the direct shoreline did we start the cable. Well, if we went directly to the shoreline, that means that we had, let me go to the previous page here to show you. And I have to move this stupid calculator back and forth, back and forth. Anyway, when we went directly to the shoreline, X, well, then was 0, right? Because that means that this distance shrunk up to be 0. So if X is 0, actually, let me plug in 0. You see, it costs 150,000. The other question was, what if we, part B, that is, said, what if X was all the way out here to 18? In other words, what if the cable was run all the way underneath water and that's it? So if X were 18, again, you could type in the number 18 here, hit enter, and you'll see it comes out as 173 point something. So it's about $173,000. All right. So that being said, let's go to E. Choose an appropriate domain and range for this problem. The smallest and largest values that make sense for X. I'm going to move this calculator again to the other side of the screen because I need to look at my function. What makes sense that I can plug in for values of X? Well, does it make sense that you want X to be negative? In other words, do you want this cable to go backwards? No, I'm spending a lot of money to make it go backwards. That's ridiculous. So I don't want to do that. So what makes sense for the domain, that was weird. Let me type that again, is starting at 0. You can include 0 if you want, and going all the way up to 18. And again, you can include 18 if you want. The range is, well, the range of values, how much money it's going to cost to lay the cable. To find the range, numerically, I'm going to adjust my window to go from 0 in the X value to 18 in the X value first. So I see something like this. It starts about 100, well, we said it starts on 150,000. It dips down a little bit below and then goes kind of high. And you can do one of two things. You can hit trace button and you can kind of trace out and see how low, what's the minimum cost. 143,000, 142,000 I saw just a moment there. Yeah. And then you can keep going to the right to see how high it goes. Or you could use the minimum function to find the lowest. And so that the way you could do that again is hit the second button, trace, and select minimum. I want to calculate the minimum. Then it asks you for the left side of the minimum. So let me go to the left side of the minimum. Here. I'll just go a little bit to the left. There we go. Enter, and it says, what about the right side of the minimum? Minimum? I can't say that word very well. Still sick, so I'll go right there. And it says, do you want to take a guess? I'll guess it's right there, but it's not. And it'll wiggle down to the actual minimum. The minimum occurs if X is at 4.85 miles, and the minimum cost would be 142,000. Well, and a lot of extra change. So let me go ahead and write that in. The range, in other words, the set of outputs, the realistic range, includes 142.99438 and goes all the way up to, well, when x is 18. And we figured out what that is. If you hit trace, type in 18, that's 173.06646. Okay, so that's my range. Those are all the set of outputs that it'll take on. Now, if you take a look at the second, or the very last question on this problem, it's actually asking to graph the function on the domain from part E. Use your graph to find the value of x that results in the least expensive root. And what's the cost for that root? We've just answered that question. The value for the least expensive root was given by finding the minimum, right? And you just move over here. After a lot of work, I got there. That's my left bound, right? I'm just repeating what I just did. Because I didn't save it, I need to redo this. Right bound and take a guess. That's fine. I'm just going to hit enter. So the best value for x is x roughly equals 4.85 miles. So provide the cheapest cost. The cost at that, or in other words, f of 4.85 roughly, is roughly equal to 142.99438. What does that mean? It means the cost is 100. Remember, this is in thousands of dollars, so $142,994.38. And if you look at all the values that we got before, to lay the cable directly to the shoreline and then across was $150,000. To go directly from the island to the relay station was $173,000. This is definitely cheaper than that, and that's actually the least amount that you'll have to pay. This type of application can honestly be used quite often in real situations. So this is a really neat situation.